Okay, so in tonight's class, we want to look at how we perform integration by parts. So the first part is basically what you guys have already looked at in first year. So just the intro part on how integration by parts work, how it works. And then after that, we're going to spend perhaps a couple of sessions just understanding how to use it for different type of expressions. So basically, it all comes from integration of by product rule. So that is perhaps where it comes from. But in the end, the integration by parts definition reduces to just an expression where you have, if you can have an expression, or if you can express an integral as an integral of a function u multiplying another function dv, then this integral can be evaluated or can be equated to the product of the function u with the other function v minus the integral of v, the function v, then du. So this is the definition of integration by parts. So this can be derived. To derive this, you need to look at derivative by product rule of two functions u and v. Okay, now how does it work? Well, perhaps the key thing when it comes to employing integration by parts is your choice of what becomes your u and what becomes your v. Because integration by parts works for when you have two products that you have to integrate. So it can be maybe you want to integrate x, maybe you have cos x dx. So the only question here becomes which part of this expression becomes your u, and which part of this expression becomes your dv. Now, what you have to see here is if you make a wrong choice, in most cases, it can start taking you in circles. You might have to start integrating over and over and over without really reaching an answer. What I want you guys to always do is when you pick something, if you're not very sure of the choices and how to make them, when you pick something and then you integrate the first time, you see to say it becomes a little bit even more complex, as in the integral that ends up here becomes even more complex than what you started with. Then most likely you picked a wrong choice. Try the alternative. It just might do the trick. So you want it such that after you pick your u and your dv, what ends up being here has to be something easy to integrate. So basically that is what it is when it comes to the choice of your u and your dv. So one way of looking at it, given when you have product of two terms that you have to integrate, the initial choice is which part to make as your u. That's what you want to think of. The first thing you want to do is, what do you choose between the two terms to be your u? After that, that's when you look at which part becomes your dv. The idea here is the choice must be such that the u part, what you choose to be your u, has to be something that becomes a constant after several differentiation. When you differentiate it a number of times, it has to become a constant. And then after that, the part that you choose to be your dv, in this case, it can be maybe this or maybe the other term. Let me not be specific here. But the part that you pick as your dv has to be something that you can integrate using standard integrals. So ideally, that is how you choose your u and your dv. Now, how does it work? Well, there is a method that I know you guys have looked at, that is in terms of LIATE, something like this. So of course, we use this when it comes to choosing your u. So we use this to decide which term becomes your u. This is logs. Then you have inverse trig. Then you have algebraic functions. Then you've got trig here. Then you've got exponents there. So this is telling you the order to say if you've got expressions in a function, then you want to pick log expressions to be your u. So the log part, you can set that to be your u. But if you have, let's say, an algebraic term and a trig term, then your u priority must be that your u has to be the algebraic term. Then the rest, of course, will have to be the trig, and then the dv will get to be the trig. Like, for example, when you look at this one here, where we're looking at the integral of x, then you have cos x here, dx. So for this expression here, clearly what you notice here is that you have an algebraic term here and a trig function here. So by the use of this simple term here, this expression, what you see is that you must choose u to first be what? You have algebraic and trig. So in other words, u has to be the algebraic term. So in this case, you'd say, let u be equals to the algebraic term. And then this implies that the rest of it, which is this, has to be your dv. So this implies that dv has to be equals to cos x dx. So this is how you make these choices. All in all, the u term has to be a term such that when you differentiate it a number of times, it must reduce to a constant. And in this case, you see that this is true for x. When you differentiate x, not even a number of times, just once, when you differentiate it once, you see it reduces to a constant. So here that statement holds. Okay, so with that in mind, let's look at the integral that we have indicated there. So once you pick your u and your dv, all you want to do is for each one of these, if you have your u, find its derivative. If you have your dv, find its integral. So if you have u, find the u. If you have v, find what v is. So from u, we can differentiate u with respect to x. We get 1, implying that du is equals to dx. And then from dv, we integrate there. So if dv is equals to cos x dx, then v, integrate both sides. The integral of cos is sine, so v has to be equals to sine x. So now to perform integration by parts, so we now conclude that the integral of x cos x dx. So now where there is x here, we can plug in v, because we said we said let u be equals to x. So this becomes the integral of u. Then where we have this term here, cos x dx, this now is our dv. So by parts, we see that this becomes the product of u and v, then minus the integral of v du. We already have what u is, what v is, and what du, what they are. So we can just substitute there. What is our u? Our u was x. What is our v? Our v, we got it after integrating there, that is sine x. Minus the integral of what is our v? Our v, we have sine x. Our v is sine x there. Then we have what is our du? Our du, remember du was equals to dx there. So our u is dx. So here now, observe what has happened here. What we have this side is an expression that is easy to integrate. That is something that is straightforward to integrate. So the first part is okay. That is just x sine x minus the integral of sine, that is negative cos. So this is going to become the integral of sine. This is going to become minus cos x. So this is the end of it. So we bring in that constant of integration plus c. So the final answer becomes x sine x plus cos x plus c. So this becomes the integral of x cos x. Okay, any questions there? Okay, we can, yeah.
what of like none of the, for example, you have algebraic term, a trig, but when you differentiate, it's not being reduced to a constant.
Okay, so when you differentiate, it's not giving you a constant. Okay, so a good example would be something that we're going to look at, I think, towards the very end of our description here. We're going to look at the integral of e ax, and then you have cos bx dx. Do you mean where you have an exponent and a trig, or you mean where you have algebraic and trig, but you're just not getting a constant?
Algebraic and trig, but
okay.
None of them are giving a constant.
So we're going to look at special expressions like that one, but that one is not actually even very complicated. The third example that we'll look at actually plays to exactly what you're saying. This will be one of the examples we'll do later on, but the one that you're describing where you have algebraic and trig is going to be our example. We can choose that as, we can even do that one now. I wanted to do one where you have algebraic and exponent, but let's make that same expression or that same case our next example. X squared sine x then dx. So does this work? Yeah, okay. So let's see. So by that description of the use of this, we see to say that what we pick as our u, because the first thing that you must always pick is u, is the algebraic, because what we have here is algebraic and trig. So algebraic comes first. So this is priority in terms of what u should be. So here we let u to be equals to x squared, so that from here du dx becomes equals to 2x, so that du becomes equals to 2x dx. Then what else? dv. If u is x squared, the rest has to be dv, and the rest is sine x dx. That has to be dv. So sine x dx. When we integrate there, we get v. The integral of sine is negative cos. So this is minus cos x. That is the integral of sine. So we now go to our integral. So the integral of x squared sine x dx, since we said u is x squared, or x squared is u, so where there's x squared, I put u. Where there's sine x dx, I will put dv. This is the integral that we're dealing with, and by definition, this is uv minus the integral of v du. This is just the definition of integration by parts. Next up, we can substitute our u. We found our u as, we actually defined it as x squared. So that is just x squared there. Next, we have our v. Our v is minus cos x. So the minus comes here. Then we have cos x here. Then minus this one on the middle. The integral of our v. Our v is minus cos x. Then our du. Our du is this expression. You see that the derivative du here is not a constant. The derivative of u was not a constant, which I think fits what you were trying to, what you were asking there. The derivative there came out as 2x dx. Is this what you're trying to give us?
Yes.
Okay, great. So we see that this is now minus x squared cos x. The minus and the minus here will give us a positive. Then we have the integral. The 2 here is a constant. It can come out. I can pull it out. Comes here. So that now what we're looking at is 2x. The 2, I've already written the 2. We're now looking at x. Then we have cos x here dx. We have already integrated. So I might even say plus c1, the first constant of integration. But since I am now about to perform an integral, a second integral here, it means that I will most likely introduce another constant. You can introduce a constant here, you will likely get another constant c2, but when you add them all up, those constants, they'll give you a general constant, which is C in the end. So here, I'll drop these. I'll include them later, but I can drop these. I just write the overall constant of integration. So to answer your question, when after you differentiate U the first time, it gives you something which is not a constant, like the way we saw here. Most likely what will happen there is you will have to perform the integral multiple times. We have performed the integral the first time. We have seen that in our solution, we still have the integral here. So it means that we have to use by parts again. So here we have to use integration by parts again. But do you see this? This is similar to what we did in the previous example. So I'll just get the solution from the previous example and I'll feed it where I have this integral here. So what I'll do is I'll get the solution from the previous example, because remember the previous example, it was the integral of x cos x dx, which is exactly what we have there. So in a test or in an exam, you guys will have to redo all this. But since we've already seen how that works out, I'll just get it and say, hey, if you integrate this part here, what you will get is going to be, the first term here remains unchanged. So it will be minus x squared cos x, then plus, you still have this 2 here, but this integral here, you'd have to do it again by parts, and the solution will be what we found earlier, which is this. So that will be the solution there. Since we are done with integration, we see that now we didn't have to integrate something more complicated. This was just something standard. So it would end here. I'll bring in that constant of integration now. So the final solution is minus x squared cos x plus 2x sine x plus 2 cos x plus c. That becomes my solution. Have I answered your question?
Yes.
Yeah.
Yeah.
All right, thank you. You have to see that if you had x to the power 3, maybe let's say sine x dx, if this is what you were integrating, most likely you have to reduce this over and over. You integrate the first time, it gives you something. It gives you something with an integral there. Again, by parts, it reduces. That is why when we started, I said your choice of U has to be the part such that when you differentiate it several times, it reduces to a constant. So it doesn't mean that when you differentiate it the first time, it gives you a constant. Sometimes you have to differentiate it several times to get that constant. Is that okay?
Very much.
Okay. But of course, in some special cases, this mode of hoping that when you differentiate multiple times, you will get a constant, sometimes it really just doesn't work. You find that, especially if you have, let's say you have an integral, you know, if I gave you the integral of x ln x, this will work out easily. We'll see, perhaps this is where we should go. But sometimes when you have, let's say, e to the ax, and then you have cos bx dx, clearly, regardless of what you pick here as your u, you know to say that regardless of how many times you differentiate it, it will never reduce to a constant. So the choice of you saying that it has to be something that reduces to a constant, you see to say that for a large extent, it applies if u ends up being the algebraic term. If u is not the algebraic term, then most likely it might not reduce to a constant. But you'd have to use other tricks to get the solution, especially when you're dealing with something like this. You'll see how we will approach it later on. But in the meantime, look at this one here. So let's get this to be our third example. What would you choose to be a u here? What did you choose here? Pardon? Lean X. So again, you have this. So of course, you not say, if I was to choose U to be equals to X, then obviously just on the next step, du dx, you get a constant. So U seems to be almost convenient for you to say U is equals to X. You are almost tempted to choose that. But when you look at this part here, clearly you can tell that from here, the rule says you start with logs, then inverse trig, then algebraic. So if you follow this, you see to say logs must come first, and lean is a log function. So here, lean must take what U is. So what does that imply? Let's see how it goes. Now we're saying let U be equals to lean X. If you did this, it implied that du dx, what's the derivative of lean X? One over X. So from here, we can see that du will be equals to 1 over X dx. Then next up, we have dv. dv will be whatever is left. So what is left is X and dx. So that becomes our dv. So dv will be equals to X dx. So when we perform the integral here, our v will be equals to, what is the integral of X dx? What will be the integral there?
It will be x squared over 2.
Yeah, x squared over 2. So we have everything that we need, v, u, dv, and du. So our integral of X ln X dx is now equal to, so ln u, ln v, ln X, I mean, is our u, X dx is our dv. So that now this is just uv minus the integral of v du. We perform the substitution, u and v. What is our u? Our u is ln X. Go ahead.
Yes, I'm behind. Yes.
Yeah.
That is du is equal to 1 over X dx. From there.
Yeah. You want me to explain from here, or you have a question?
Yes. Just from there, sir.
Okay.
Explain from there.
So all I did was, here we made du the subject by just cross multiplying the dx, taking it here. Then after that, I was done with du. I now went to get what dv is. Now we said we first choose what u is, and since u was selected to be ln X, since this is what u is, the rest of the expression has to be dv. The rest becomes X and dx. So dv becomes X dx. That becomes our dv. So from here, from dv, we want to find what v is. So we then integrated both sides. The integral of dv will just be v. The integral of X dx became X squared over 2. So that is what we did. From there, we then brought everything to the definition of integration by parts. This is the definition here. Now I am just substituting. Is that okay?
Yes, sir.
Okay. So we're substituting our u. Our u, we picked u to be ln X. Then v, from the integral, v ended up being X squared over 2. So you really don't want to put X squared here. If you put X squared here, then the ln X has to be in brackets, because the fear is you will forget and end up multiplying these two here. So instead, I'll put everything else that comes before the ln. So I'll say ln squared, then over 2 here. So once you're done with that, I'm done with my u and the v there. So this will be minus the integral of v comes first. V is x squared over 2. So I have x squared over 2 there. Then we have our du. From here, what is our du? Our du is 1 over x there. So our du is 1 over x. So you have multiplying 1 over x. Then we have dx there. You see why we picked u to be the ln, because after that, this and this cancels out, the 2 comes out, we now have this squared ln x over 2 minus the 1 over 2 comes out, then we have the integral of x dx. Guess what? This is way too easy to integrate. We can easily integrate that one, and the answer becomes x squared ln x over 2 minus the integral of x. You saw it earlier on. It's x squared over 2. So since this is the last one, plus that constant of integration, c. So the final answer becomes x squared ln x over 2 minus x squared over 4, then plus c. So this becomes the overall integral. Now, I want you guys to try the same one. Try to perform the same integral x ln x dx, but this time just try to see what would happen had you picked u to be not ln, u to be x. Would it be would it be the way this one was? The idea of what this rule is such that the integral becomes easy to evaluate. It should be the easiest, it should be easy to evaluate, yes. Now, try to see if you can work it out with u being equals to x. Try to see if it will be easier than what we had. But from what that rule says, it will be a little bit more difficult if you chose this path. But I'll let you guys experiment with it. Or would you guys want us to do it together?
We can experiment.
Okay, so you guys will experiment. Okay, that's great. Okay, so what else can we do? Okay, so we've done a number of these. I really don't want to go very far. There are a few more that we can look at. This is the third one. Let me write down 4. You guys can try this one out. So this is the integral of, it's another basic one, 3t e to the 2t dt. So you can try this one out. It's, of course, algebraic exponent there. You know which one becomes your u there. Then perhaps the tricky one that we see is going to be number 5, which is the integral. If you have something like e to the x, then you have cos bx here, dx. So this is something general. By making sure that these are not exact values, we're keeping it general so that you know how to apply the same way, or the same method of integration to anything which is a combination of an exponent and a trig function. So this method is going to work for a combination of an exponent and a trig function. Now, can we do this one, or you guys want to try it out later? Can we make this the last one for tonight?
You can try it out later.
Or you can try it out later. Okay, so then you guys can try out this one tonight. Then we can start with this one tomorrow night and maybe look at a few more questions that maybe work on the same concept before we move on to row reduction. Okay, so with that in mind,
Should we add values, or we just work it out as it is?
As it is. As it is.
Okay.
Yeah.
Okay.
Okay. All right, guys. So yeah, feel free to invite your friends. Currently we are 70, which is a good number, but invite more of your friends. I think, yeah, let's be more. The more the merrier. So let's be more and let's see if we can benefit together. If you guys can actually exceed 40 here, then I can say we can also start doing one of either triple E or CEE. Can start doing that one for free as well. But now I think 40 is too small. Let's exceed 50. Then we can bring in triple E and C or triple E or CEE for free as well. All right, guys. Have a good night. See you in the quiz. Those who are doing the quiz. Yeah.
I have a question.
Go ahead.
Listen, for me, I was requesting after this integration part, can we go back to application of differentiation? Never understood any of this, but especially linearization, orbital room, they kind of never got the idea.
Okay. So we can finish up integrals in their applications, perhaps. Then after that, we can go back to help you guys revise. Since you guys are preparing for, you have a quiz. Is that a quiz or a test coming up soon?
A test.
Yeah. So yeah, we can finish up integrals, then we can track back.
Okay. Thank you very much.
Bye, guys. Have a good night.
Yes, sir.
Yeah.
Before you go, sir.
Okay.
Yeah, when there was my Chan, race theorems and my Chan, my Taylor's Chan, something like that. Those are conditions. Thank you.
Yeah.
Process for differentiation.
Uh-huh.
I think we should go back to those.
Yeah, I think that's what your friend was saying there as well. So we'll finish integrals and the application of integrals. After that, we'll go back and look at those.
Thank you, sir.
All right, guys. Bye now.